Okay, here we are on page 3 of the addendum for probability. First, we talk about Bayes' theorem, which basically builds on the conditional probability equation. We know that the probability of the event A happening given that B already happened is the probability that both A and B happened divided by the probability that B happened. And if we multiply both sides by the probability of B, then we're going to get this equation here. And if we reverse the A's and B's, we get this equation here. And we can see that actually the left side of this equation is the same in both cases. So we could set them equal to each other, and that gives us Bayes' theorem. Okay? All right, so let's look at number 1. Coffee machines A and B produce coffee in identically shaped plastic cups. A produces 65% of the coffee sold each day, and B produces the remainder. A underfills a cup 4% of the time, while B underfills a cup 5% of the time. So basically, let's see, B produces 35% of the coffee sold each day. Okay. A cup of coffee is chosen at random. Find the probability that it is underfilled. Okay, so the probability that it is underfilled is equal to the probability that it's underfilled given that it is coffee A times the probability that it's coffee A plus the probability that it's underfilled given that it's coffee B times the probability that it is coffee B. So the probability that's underfilled given coffee A is 4%, and the probability that it is A is 65, and then the probability that's underfilled given that it's coffee B is 0.05, and the probability that it is coffee B is 0.35. So let's see, it's 0.04 times 0.65 plus 0.05 times 0.35. 0.0435. So it's 4.35% basically. Okay, let's take a look at part B. A cup of coffee is randomly chosen and is found to be underfilled. Find the probability that came from A. So what's the probability that it is coffee A given that it is underfilled? So remember that the probability that it is A given that it's underfilled is, let's see, is kind of related to the probability it's underfilled given that it's A. All we need to do is multiply it times probability of underfilled, and then we set that equal to the probability it's underfilled given A times probability it's A, because both of these are related to the probability that it's A and it's underfilled. Okay, so probability that it's underfilled, we already know it's 0.0435 because we just calculated that, and it's no accident that they asked us to calculate that. They're actually being nice to us. They're telling us what to do. The probability it's underfilled given that it's coffee A, we already know that it's 0.04. The probability that it is A is 0.65. So now we can find the probability that it's A given that it's underfilled by dividing this divided by that. Okay, so 0.04 times 0.65 is 0.026 divided by 0.0435 0.598. Okay, and whenever you do one of these problems on an exam, you should probably try to show this step here, okay, before you get to this step here, so that you could show what you divided to get to that. In case that you make some kind of mistake in the arithmetic, you might get credit for having the numerator and denominator correct. Number 3. A marble is randomly chosen from a can containing 3 reds and 5 blue marbles. It is replaced by 2 marbles of the other color. Another marble is then randomly chosen from the can. If the marbles chosen are the same color, what is the probability they are both blue? This is an ideal candidate to draw a probability tree. So let's first say, okay, we are going to draw either a red marble or a blue marble. And what is the chance that we will draw a red marble? It will be 3 out of a total of 8 marbles. And the probability that we will draw a blue marble would be 5 out of 8. And then the second marble drawn would have a different probability, because when we draw out a red marble, instead of replacing it back, we are going to replace it with 2 of the opposite color. So when we choose a red marble, instead of 3 red, 5 blue, the next time it's going to have 2 red and 7 blue, because we're going to replace the third red marble with 2 extra blue marbles. So the chance we're going to get red the second time would be 2/9 instead of 3/8. And the chance we would get a blue would be 7/9. And then in the second branches here, after we draw out a blue, then the distribution is going to be 4 blue, because we don't put back the blue, we put in 2 additional reds. So then we would have 5 red and 4 blues. So what are the chances that we would choose a red the second time? It would be 5/9. And the chance that we'll choose a blue the second time would be 4/9. Okay. So the probability of each one of these happening, like for example, red 1, red 2, the probability of that happening would be 6/72. The probability that we would have red 1, blue 2 would be 21/72. The probability that we would have blue 1, red 2 would be 25/72. And the probability that we would have B1, B2 would be 20/72. Okay. So let's see what they want to ask us. So if the marbles chosen are the same color, what is the probability that they are both blue? Well, if they're both the same color, that would be this outcome and this outcome. So given that they're the same color, so what's the probability that they are both blue given that they're the same color? So that would be B1, B2 or R1, R2. So what's the probability that they are B1, B2 and they're the same color, divided by the probability that they are the same color? Okay, so the probability that they're the same color would be R1, R2 plus B1, B2, so that would be 26/72. The probability that it is B1, B2 and it's the same color, well, B1, B2, it's the same color, so it would be 20/72, and we wouldn't need to modify that. that would be equal to 20 divided by 26, which is equal to 10 divided by 13. Okay? Number 5. A new blood test has been designed to detect a form of cancer. The probability that the test correctly identifies someone with cancer is 0.97. The probability that the test correctly identifies someone without cancer is 0.93. Approximately 0.1% of the general population are known to contract this cancer. When a patient has a blood test, the test results are positive for cancer. Find the probability that the patient actually has the cancer. This is one of the most commonly misunderstood probability applications in real life. This is the reason why whenever you get a positive test result on any kind of medical exam, the doctor immediately orders another test to confirm the result, because the probability of this happening one time, it's more probable for the test to be wrong than for you to actually have the cancer. So they need to do it again to make sure that you indeed have the cancer. Okay? So, okay, let's take a look at this. The probability that the test correctly identifies someone with cancer is 0.97. So the probability that it's positive, given that the patient actually has cancer, is 0.97. The probability that the test gives negative when you don't have cancer is 0.93. Okay. And 0.1% of the general population are known to contract this cancer. So the probability to have this cancer is 0.001. Okay. Let's try to make a tree diagram. So the first thing that happens is either the patient has cancer or does not have cancer. The probability that they do have cancer is very small. It's 0.001. The probability that they don't have cancer is quite large. It is 0.999. Okay. The probability that, given that they have cancer, that the test correctly identifies them is 0.97. The probability then that they are incorrectly identified is 0.03. And the probability that they are correctly identified, instead of N, I'm going to put P dash, okay? P dash. The probability that's P dash, given that it's C dash, is 0.93. And this would be 0.07. So let's find the probability of each one of these. So C and positive would be 0.000, oh my gosh. So it would be 0.97, and I'm going to move the decimal point 3 back. So it would be something like that, okay? What's the probability that they don't detect it? It would be 0.00003. What's the probability no cancer and detected it? It's actually pretty big, isn't it? It's 0.999 times 0.93. 0.929. What's the probability that they don't have cancer and they detected it correctly? Oh, I'm sorry. 0.92907 is here. Right? What's the probability that they don't have cancer and they accidentally identified it as cancer? Then it would be 0.999 times 0.07. And this is kind of big. 0.06993. Okay. Now, let's do the analysis. So when a patient has a blood test, the test results are positive for cancer. Find the probability that the patient actually has the cancer. So testing positive for cancer is this outcome, and it's this outcome. And you can see that actually the probability that they don't have cancer is much larger than the probability that they have cancer relatively, right? So what's the probability that they actually have cancer given that they tested positive? So let's say so that would be equal to the probability that they have cancer, 0.00097, and they test positive, divided by the probability that they tested positive, which would be 0.00097 plus 0.06993. So let's see what the denominator is. 0.06993 add together with 0.00097, and we get 0.0709 for the denominator, and the numerator is 0.00097. So the probability that they actually have cancer, given that they tested positive for cancer, is actually 1.3%. It's very small, right? Which is why they always repeat the test. 1368. Okay? Let's check to make sure that answer is correct. Number 5. Yes. Okay. That's it for this page.